All right, IBAISL2. Today we're back to talk about some applications of calculus. So I know we've been doing derivatives and integrals or integration, but today I'm mainly going to focus on derivatives. So our first example is two numbers that have a sum of 10. What is the maximum value of their product? Let's just say that one of the numbers is x and the other number is going to be 10 minus x. So, if x was 1, then the other number would be 9. If x was 2, the other number would be 8. I realize you could probably set up a table for this pretty quick. I mean, there's not many combinations, and you could just multiply them all and see which combo adds to 10 and has the biggest product. But once again, we're going to focus on the derivative way of doing things. So let's say that their product is equal to the two numbers multiplied together. So there's very similar steps with a lot of these problems where you try to come up with a model for the problem. So then you try to take the derivative of that model and then set it equal to 0, because that's when the derivative is equal to 0 is when the graph of the function would have maximums or minimums. So we'll say that the product is 10x minus x squared. And then if we find dp dx, which is the same thing as p prime, it's just the derivative, this would be 10 minus 2x. Now, if you take that and you set it equal to 0, so I'll do that off to the side here. 0 is equal to 10 minus 2x, and then we solve by subtracting 10 from both sides, dividing by negative 2, we get that x is equal to 5. If you put 5 back into this right here, you get 10 minus 5, so the other number is also 5. To prove that we found a maximum and not a minimum, you can do what I call a little zone test. So the number that we found, 5, is going to go right here. I'll call this a zone test. Then you can pick a number to the left of 5 and a number to the right of 5 and plug it into the derivative to see what's happening with the slope of the function on either side there. So if I pick a 4 on this side and a 6 on this side, if I plug a 4 into the derivative, which here, I'll just call it p prime over here, you get 10 minus 2 times 4, which is 2, which is a positive number. So what that means is in this zone over here, to the left of 5, that we are getting positive slopes. Then if you take 6 and put it into the derivative, you get 10 minus 2 times 6, which is negative 2, which means on this side of the 0 we found in the derivative, there are negative slopes. Now, if you can picture a function that has positive slopes to the left and negative slopes to the right, that means that the function is going uphill on this side, and then at 5, it has a maximum, and then goes downhill. So it looks something like this. What that means is, at 5, we found a maximum. So the answer is 5 and 5. Next up. Find the most economical shape, which means minimum surface area, for a box with a square base, vertical sides, and an open top. So notice in my diagram that I drew, there's no top on this box. But the whole thing must contain 4 liters. First thing we're going to do is we're going to label the base as x times x, and then the height we don't know, so we'll just call it y. But we do know that volume equals area of base times the height. So that means volume is x times y. And we need volume to be Hold on. Sorry, just a second. Why are they switching to centimeters? Sure, whatever. Okay. You know what? I'm just going to change the original problem, and then I'm going to say that it must contain 4,000 centimeters cubed. What happened is they said that it should be 4 liters, and then they want to do everything in centimeters, so they do like a unit conversion on the 4 liters to change it into 4,000 centimeters, but we haven't focused on unit conversion too much, so I'm just going to make that 4,000 centimeters cubed. So what we have to do is set that 4,000 equal to x squared y, and then if you solve for y, that means y is equal to 4,000 divided by x squared. Now for the surface area of this box, which we're going to call A of x. It's this side, which is x times y, but then there's 4 of those. Like there's one on that side, there's another one on this side, that's also x times y. There's one in the back, that's x times y, and there's one on the side, that's x times y. So we get 4xy, and then the last part, since there's no top, there's just a bottom, is there's a base of x squared. So we get 4xy plus x squared. Now, it's not, you can't do derivatives really when there's 2 variables involved in the equation. So since there's a mix of x and y's, we need to try to get it down to just an x variable in there. So what we do is take the y that we already solved for, and we're going to plug it in for this y right here. So the surface area equation is 4x times 4,000 over x squared plus x squared. Now, if you simplify, oh, come on, buddy. This x and this x squared, that's one set of x's that cancel each other out. So we can actually clean up this model a little bit and say a of x is equal to, well, the 4 times 4,000 would be 16,000. So we'll get 16,000 over x plus x squared. Now, this is the model for the surface area that we need to take the derivative of. So before we take the derivative, you have to do a little rewrite with that x in the denominator and say this is 16 grand x to the negative 1 plus x squared. And then you can get a prime x. So a prime of x is equal to, remember, bring the negative 1 out in front and get negative 16,000. And then this will be x to the negative 2 plus 2x. Yeah. Now, when you go to set this equal to 0, so then we're going to have to set it equal to 0 and solve. So we get 0 equals negative 16,000 x to the negative 2 plus 2x. Up here on this problem, it wasn't too bad solving because we really just had to solve 0 is equal to 10 minus 2x, which is like not too bad to solve at all. You subtract 10, you divide by negative 2. But then if we go back here, this is hard to solve. So we're going to say this is we're going to do this on the calculator. So on the calculator, you need to graph that, set it equal to 0, and then using technology, you can figure out that 20 is equal to x. Then if you do a zone test, and you put 20 right here, which is our one solution that we found, we need to confirm that this is a minimum that we found and not a maximum. So using our derivative, you would just pick a value, and it doesn't have to be right next to 20. Like you could pick they don't even have to be the same distance apart. Like you could pick 0 on this side, and you could pick, I don't know, 22 on this side, anything that's to the left and to the right. But when you plug them into the derivative, you should get a negative number on this side and a positive number on this side, which means that it's going downhill on this side, and then at 20, it bottoms out and then turns uphill on this side. So this confirms that this is a minimum. So that means x was the base of the box, and then y was the side. So if you put 20 into this function right here to find the y, you get 4,000 divided by 20 squared is equal to y. So I believe this is 10 when you simplify that on your calculator. So our final answer is that the box needs to be 20 centimeters by 20 centimeters by 10 centimeters to produce a minimum surface area on the box. Last problem. Square corners are cut from a piece of 12 by 12 tin plate, which is bent into an open dish. What size squares should be removed if the volume is to be at a maximum? Okay, here we go. First of all, I drew a picture where this was a square that was 12 by 12, but then we're going to take these little corners out of it, like where this is x, x. These are all little x by x squares, which means that this side right here is going to be 12 take away 2x, because you subtract, like the whole entire side was 12, but then if you take the 2x's off the corners, it's 12 minus 2x. That's going to be the same for this side right here. That's also going to be 12 minus 2x. So we're going to write a model for this. We're going to call it v of x for volume. Now, when you fold this box up into like an open dish, like it says, it will look something like this. Excuse my crude drawing, it's getting a little wobbly. Where this side is 12 minus 2x, this side is 12 minus 2x, and the height of it will just be the size of those squares, which is x. So to find the volume, it's the area of the base, which is 12 minus 2x times 12 minus 2x, and then times x. The next step would be to take the derivative of this model, but we can't take the derivative when it's in this form. We have to multiply it all out before we can use the power rule. So if you FOIL the first two things, you get 144 minus 48x plus 4x squared, and that's still times x. So then you have to multiply everything by x, and you get 144x minus 48x squared plus 4x cubed. Then we can take the derivative of that model and say v prime of x is equal to 144 minus 96x plus 12x squared. Now, when you set this equal to 0 to try to find any minimums or maximums, I'm not going to take your graphing calculators away from you because, yeah, I want you guys to have them on the test. So know that this problem could be factored by hand, that this is nicely factorable. But I'm fine with you guys graphing that and then using the 0 function on your calculator. And when you do, you are going to get that x is 2 and 6. I mean, I'll show you the factored way too, that you could pull a 12 out of everything. And then there's x squared minus 8x plus 12 left inside. And then you get two numbers that multiply to positive 12 and add to negative 8 are negative 2 and negative 6. So you get x minus 2 and x minus 6. So then when you set everything equal to 0, you get x is equal to 2 and 6. Now, you guys, both of these answers don't make sense. There's only one of them that makes sense. If you picture the squares being 2 and 6, if you go back to this right here, picture that this distance here is 6 and this distance is 6, but the whole thing is 12. That doesn't make sense, because if you go 6 over here and 6 over here, there's like, you'd be cutting the entire paper in half. Like, it doesn't create anything with a volume. So that's actually probably a minimum that we found for the 6. So we're going to cross that guy out and say we're just using 2. Quick zone test. Put a 2 down here. Use your your derivative, the original one. So this is 144 minus 96x plus 12x squared. And then throw a couple numbers in there, like 0 and 4 or something like that. When you do that, you'll find a positive number on this side and a negative number on this side, which means it's going uphill on this side, and then it reaches a maximum and then goes down. So we did indeed find a maximum. So maximum when 2 centimeter by 2 centimeter squares are cut out. All right, you guys, those are our 3 application problems today. Good luck with your homework.